For centuries, we looked up at the night sky and it just seemed, well, chaotic. You had planets wandering around, going forwards, then backwards. It didn't seem to make any sense at all. But what if there was a hidden script, a set of rules for this cosmic dance? Turns out there is. And today, we're going to break down the 3 simple laws that revealed the beautiful order behind it all.
So, this was the big question, right? The one that kept astronomers up at night for generations. They'd watch planets like Mars trace these crazy looping paths across the sky, and it just looked like a total mess. But they had this gut feeling that underneath all that chaos, there had to be some deep, elegant pattern just waiting to be found.
Okay, so for something like 2,000 years, everybody bought into one single idea. The heavens are perfect, and the most perfect shape is a circle. So obviously, planets had to move in perfect circles. Simple, right? Well, there was one little problem. The data never, ever fit. And then along comes this guy, Johannes Kepler. He dared to ask, hey, what if the ancient beliefs are wrong and the data is right? And he discovered that planets don't move in circles at all. They move in ellipses, a slightly stretched out and frankly way more interesting shape. And that one discovery, it completely rewrote the book on how the universe works. So Kepler laid out these 3 incredible rules that run the whole show. Let's start with the first one, the rule that defines the actual path of every planet's journey. We call it the law of orbits. So what's an ellipse? Just think of a circle that you've kind of squashed a little bit. But here's the crucial twist. A circle has one center point. An ellipse has 2 special points inside it called foci. And here's the revolutionary part. The sun isn't in the dead center of the orbit. No, it sits at one of those 2 focal points. And that seemingly tiny detail, well, it changes absolutely everything. Right, so because the sun is off-center, a planet's trip around it is never the same distance. It's always getting a little bit closer to the sun and then a little bit farther away, over and over and over again. That old idea of a planet just cruising along at a nice, steady distance, totally wrong. And these extreme points in the orbit, they've got special names. When a planet gets as close as it's going to get to the sun, we call that its perihelion. And when it swings all the way out to its most distant point, that's its aphelion. Every single planet, including us here on Earth, has these 2 key moments in its annual dance. Okay, so if a planet's distance from the sun is always changing, does that affect anything else? Oh, you bet it does. And this brings us right to Kepler's second rule, the law of areas, which is all about one thing: speed. This was another massive break from the old way of thinking. I mean, it's easy to picture a planet just kind of coasting along at the same speed forever. But Kepler's math proved that was completely wrong. A planet's speed is always changing. It's speeding up and slowing down all throughout its orbit. Now, the official wording of this law, yeah, it sounds a little intimidating. A line joining a planet and the sun sweeps out equal areas in equal intervals of time. I know, it's a mouthful. But what it's really describing is a super elegant relationship between where a planet is and how fast it's moving. Let's just break down what that actually means. Here's the simple takeaway. The only thing you really need to remember. When a planet gets closer to the sun, where gravity is pulling on it the hardest, it speeds up. It absolutely whips around that part of its orbit. Then, as it swings farther away, it slows way, way down, moving at its most chill, leisurely pace, before gravity pulls it back in to speed up all over again. It's this endless cosmic rhythm of hurry up and wait. And this isn't just some random fluke. It's a fundamental law of physics called the conservation of angular momentum. The best way to picture it? Think of an ice skater spinning. When she pulls her arms in tight, her spin gets crazy fast, right? A planet does the exact same thing. As gravity pulls it closer to the sun, it's like it's pulling in its arms, and its orbital speed just has to increase. All right, so we've got the shape of the orbit, and we've got the speed of the planet. Kepler's third and final law. Man, this is the one that ties the entire solar system together. It's the master rule, the hidden rhythm that connects every single planet to every other planet. This is the law of periods. This law is wonderfully simple. It basically says that the farther a planet is from the sun, the longer its year is going to be. I mean, it just makes sense, doesn't it? Take Mercury, the closest planet. It zips around the sun in just 88 days. Compare that to Neptune, way out in the cheap seats. It takes a whopping 165 years for Neptune to make a single trip. But Kepler didn't just stop at farther means longer. He figured out the exact mathematical relationship. He found that if you take a planet's orbital period, its year, and square it, that number is directly proportional to its average distance from the sun, cubed. Now, you don't have to memorize the formula. The amazing part is that for the first time in history, there was a single, predictable equation that perfectly described the motion of every known planet. It was the key that unlocked the whole solar system. So, the shape, the speed, and the rhythm. When you put these three laws together, they were so much more than just clever observations. They completely, and I mean completely, changed how we see the universe and our place in it. Their impact was just massive. First off, they provided the hard, undeniable math that proved the sun was the center of the solar system. Then, decades later, some guy named Isaac Newton came along and used Kepler's laws as the bedrock for his own theory of universal gravitation. And their legacy is still with us today. Literally, every time we launch a satellite or send a probe to Mars, we are using these same 400-year-old rules to plot the course. You've got to remember, Kepler was a deeply religious man. To him, this wasn't just science. It was almost a spiritual mission. He believed that by discovering these laws, he was actually getting a glimpse into the mind of God. This quote just says it all. He saw this beautiful, divine math woven into the very fabric of creation. And that leaves us with one last, really powerful thought. By simply trusting the data over ancient beliefs, Kepler found the hidden operating manual for our entire solar system. And it just makes you wonder, doesn't it? What other fundamental rule books are still out there, governing everything from quantum particles to entire galaxies, just waiting for someone to come along and finally read them?